Hi, we're back with the second video in chapter 18, and this one talks about Coulomb's law. So you can see we're on section 3 in chapter 18. So the French physicist Charles Coulomb investigated electric forces. This can be a very daunting task, and so what he did is because he was unable to measure the exact charges, his technology wasn't there yet. What Coulomb did is he looked at charge ratios, and we'll talk about those in just a minute, and tried to decide how strong the forces were based on the charge ratios. So he used something called a torsion balance. That's what this diagram is all about. You have a rod, and at either end there are metal balls, and then you have the ability to lower a charged ball down into the device. It's protected from wind currents and has a scale on the side of it to allow you to measure how far it twists as it turns. This rod is attached to a thin fiber, so it can twist. If it's attracted to the charge ball B that you've inserted, it'll swing towards it. If it's repelled, it'll swing away from it. By measuring the amount of attraction and repulsion by the amount of swing, he was able to come up with equations that allowed him to calculate the relative forces. So it's really a clever little device. All right, so as we move down, let's look at those charge ratios. So suppose we have 4 balls and they're exactly the same. They're identical, same size, same mass, same composition. And we put a 100 Coulomb charge on the first ball. So that's why this first one has a 100C in the middle of it. And we don't let any of them touch. And then suppose we touch ball 1 to ball 2. What happens is because the balls are identical, the charge is shared equally. So instead of the 100 Coulomb staying on ball 1, it's split, and half of it goes to ball 2. And so we now have a 50 Coulomb charge on ball 1 and a 50 Coulomb charge on ball 2. Suppose we want to take ball 2 and let it touch ball 3. What happens? Well, again, because they're identical, they split evenly. So 25 coulombs will stay on ball 2 and 25 will go to ball 3. Ball 1 remains unchanged because it was not part of the scenario. It didn't get disturbed again. So ball 4 has 0 coulombs, ball 3 has 25, ball 2 has 25, ball 1 has 50. If we touched ball 4 to ball 3, there'd be 12.5 coulombs on each of them. If we touch ball 4 instead to ball 1 would now have 25, ball 4 would have 25. So you have the ability to split and split and split depending on how many times you touch the charged object with an uncharged object. And there'll be some example problems in the study guide that you'll want to pay attention to. All right, so that tells us how we ended up with charge ratios. With Coulomb, he didn't know it was 100 coulombs. He just said Q. So you'd start out with Q and then have Q divided by 2. And then these two would be Q divided by 4. And the first one would still be Q divided by 2. But I find my students don't care for those ratios. So we picked numbers. All right, the result of all of this experimentation was that Coulomb came up with an equation, a formula to allow us to calculate the force that 2 electric charges feel when they are attracted or repelled by each other. We call this Coulomb's law, and it's the electric force, and it is equal to, so it's capital F, that's a symbol we've used before for force. Capital F is equal to little k, lowercase k, multiplied by Q1, multiplied by Q2, And so then that whole numerator is divided by the square of the separation distance. And we'll do some numeric examples, so don't panic yet. You can see that F is the force. It would be measured in newtons because we measure force in newtons. Q1 and Q2 are charges, so they have to be measured in coulombs. R is a distance, so it has to be measured in meters. Little k is a brand new constant for us. Little k is equal to 9 times 10 to the 9th Newton meter squared per coulomb squared. You do not need to memorize little k's value. It'll be provided for you on the quiz. So Coulomb's law is F equals K, Q1, Q2 over R squared. And these charges, again, are measured in coulombs, or they might be measured in nanocoulombs or microcoulombs. So we have to be careful about that. We normally don't care about the plus or minus on the Q as far as getting the value for the force. Force is a vector. And so what we'll first do is find its value. How big is it? Its magnitude. And then after we know how big it is, we'll actually look at those two charges and then decide which way does the force point. And that all depends on which charge we're talking about the force acting on. Does it act on charge 1 or charge 2? The numeric value, the magnitude, will be the same, but the way it points will vary depending on whether we're talking about the force on charge 1 because of charge 2 or the force on charge 2 because of charge 1. All right. So we're going to use the absolute value of the charges, and then only when we pick a direction will we care about whether they're plus or minus. So let's look at that before we do any numbers. We have to know which way the forces point. Whoops, again, I think I overshot just a tad. So let's back it up. Suppose we know that charge 1 is a positive charge and charge 2 is a positive charge. We don't really care how big they are. We just care, are they plus or minus? So the first question is, which way will charge 1 move because of charge 2? Which way will the force on charge 1 be because of charge 1? Which way will it point because of charge 2? Well, they repel each other. They are like charges, so they repel. And what that means is charge 1 is going to move away from charge 2. So to move away, that means charge 1 will go left. So which way will charge 1 move because of charge 2? Well, we know it's going to go left. Which way will charge 2 move because of charge 1? Charge 2 is going to go which way? We know it's going to go to the right. It will be repelled. So the direction depends entirely on which charge are you talking about. Are you talking about charge 1 or are you talking about charge 2? It makes a difference whether they go right or left. All right, let's look at our second case. We've got opposite charges. Charge 1 is positive, charge 2 is negative. Which way is charge 1 going to move because of charge 2? Charge 1 is going to be attracted to charge 2. Opposites attract. So that means charge 1 is going to go right because charge 2 is there. Suppose we want to know which way will charge 2 move because of charge 1. Charge 2 is going to be attracted to charge 1 because, again, they're opposites. So opposites attract. That means charge 2 is going to go left. So again, it depends on which charge are you talking about doing the moving, and are they opposite charges or like charges? All right. Again, there'll be some practice examples in the study guide. So let's talk a little bit about the electric field. We know which way electric forces will point based on the type of charge you have. Now we want to talk about the electric field. So forces that act over a distance, and that's like the gravitational force. You know, you pick up a ball and you drop it, it falls down because gravity pulls it towards the center of the earth. It acts over a distance, and so it's considered a force field. So forces that act over a distance are thought of as fields. Gravity produces a force field. There are magnetic force fields. There are electric force fields. You hitting a golf ball is not a force field. That's a contact force. You have to make physical contact for the ball to move. All right, so the magnitude, and we have Faraday to thank for the concept of a force field, for forces acting over distances. The magnitude and direction of your electric field is going to be defined in terms of the effect it has on a positive test charge. So by definition, in physics, a test charge is going to be positive. It'll have another qualifier on it in a minute. We've already talked about the electric force. F equals K, Q1, Q2 over R squared. Now we have a formula for electric field. E is equal to F divided by Q, but we're going to simplify that. So electric field is also a vector. It's measured in newtons divided by coulombs, forces in newtons and charges in coulombs, so it's a newton divided by a coulomb. In this equation, F is the electric force, little q is the test charge. We've already said the test charge has to be positive. The second restriction on the test charge is that it is very, very small. The reason we do that is we don't want the test charge to change the charge configuration. We don't want charges to move because the test charge is there. The test charge is only used to help us pick the direction for the electric field. So the direction of the electric field is the direction the positive test charge would move if it's being acted on by those other charges. So we'll look at that in just a second. All right, we said that E was F over Q, but we know that F is K, Q1, Q2 over R squared. So we're going to make our Q2 the test charge. That means when we plug it in, Q test cancels. Well, that's good because our test charge can't change things. It just is used to give us the direction. And that means that E, besides being written as F over Q, could be written as K, Q1 over R squared. So it's little k, that 9 times 10 to the 9th Newton meter squared per coulomb squared, multiplied by your charge, Q, divided by, now this is not the test charge, remember test charge got canceled out, and then divided by the square of the separation distance. Well, in the past, R was the distance between two charges. Now, R is the distance between the point you're asking about and charge 1. So we'll look at it in just a second. Electric field can be due to more than one charge. And if that's true, what you do is you look at each contribution and then we add them as vectors. We'll do some examples of this in case you don't remember how we did that last semester. So let's start out with our cases. So we have a charge and we know it's a positive charge. Right now we don't care how big it is, we just care is it positive or negative. And we want to know which way is the electric field pointing at point A. So here is point A, this blue dot. There's no charge there. We're going to pretend that we have our positive test charge at point A. And so to decide the direction of the electric field, we have to ask ourselves, which way would a positive test charge move if it were at point A and it encountered charge 1 at some distance? And so to find the direction, all we have to know is charge 1 positive or negative? And so we look at point A and we say, okay, our test charge is tiny and positive. Which way would it move because charge 1 is there? So if point A has our pretend positive test charge, it would be repelled by charge 1. Like charges repel, likes repel, and so the electric field points to the right. Our free positive test charge at point A would move away from charge 1. Suppose we're down here at charge, when we've got charge 1 is a negative charge. Point A is still our pretend free positive test charge. Remember, there's not really a charge here. It's a pretend positive test charge. What would a pretend positive charge do because charge 1 is there? Well, charge 1 is negative. Our pretend test charge is positive. Opposites attract. And so what that means is that our E field points left. Our free positive test charge would be attracted to our negative charge. It would go left. All right. Let's look at our electric field lines. So we've already decided which way the electric field points. Now let's talk about electric field lines. We use these to give us a picture to try to show which way the electric field is pointing. And we have some rules. We'll draw some of this again in our first lab. So they begin on positive charges. They never, this one's got a little mistake. This top curved part should have started on the plus charge. It just didn't get down far enough. I wonder if I can move it. No, probably not. All right, so they begin on positive charges and end on negative charges, or they go to infinity if you've got an isolated charge. Arrows indicate the direction, so we're going from positive to negative. They indicate the path that your free positive test charge would travel in. And the lines have to intersect the surface of your conductor at right angles. So this one is pretty straightforward. They come from some positive place in space and they're pointing towards this negative charge and they hit it at a 90-degree angle. These not so much. This one doesn't really look 90 degrees. It's kind of wacky, and so is that one. And again, these are not perfect. You can see I drew them on the computer. There are better diagrams in the book. So in the book, you can look at page 777, which is figure 18.23. These page numbers vary depending on if you're looking at the page number of the PDF itself or the page number of the textbook. So I usually give the textbook pages. Those would be when you looked at an actual page, it would be in the upper right or left-hand corner of the page. It's best if you download the book. I'll talk about this in another video. All right, so again, we'll do some more with these diagrams in our first lab. We'll work on them. Insulators and conductors. We've got matter that falls into one of three categories. It can be, we can classify it as a conductor, an insulator, or a semiconductor. Conductors have lots of free electrons, so they conduct electric charge easily. Typical things that are good conductors are usually metals. Insulators do not conduct electricity. They normally hang on to their electrons pretty tightly. Pure water, which we are not going to encounter, is a good insulator. Glass, cloth, wood, things of this nature. And then we have semiconductors. Semiconductors are used in electronics, and they conduct electricity only under certain specific conditions. Silicon, germanium, carbon, they have some free electrons, and you can control which way the electricity moves because of it. All right, we're going to stop video 2 here, and we'll pick up with charge by conduction and induction in video 3. So we will stop the share, and we will stop